absorption, I should have continued with heterogeneous catalysis, but I do not know how I came to colloids. Anyway, after filling colloids, I'll go to the heterogeneous catalysis. But it is a serious mistake that I have done because it has some relation with the absorption. But anyway, no problem. So we have uh, discussed about the classification of colloids, and there we found that colloids can be classified on different merits. So we have discussed there are three types of colloids. One depending upon the physical state of the dispersed phase in dispersion medium, and there we found that we can classify them into 8 categories. Then on the nature of interaction dispersed phase phases have with the dispersion medium, on the basis of that it can be classified into 2 categories, lyophilic and lyophobic colloids. Lyophilic colloids are also called reversible colloids, and lyophobic we call them as irreversible colloids. And the last one that we have discussed, that is the chemical classification based on their method of formation. So there we found that it can be classified into 3 categories, and that entirely depends upon their sizes. So depends upon how they acquire that size of the colloid. One may be because of its own size. So that in that case, the molecule should be very big, and we call them as macromolecular colloids. Second, we have some particles or atoms or molecules which are alone or independently not stable. So they club together for their dependence. And on the because of that, they always move around in clusters and acquire a larger aggregated shape, and we call them as multimolecular colloids. We find generally the uh, colloids that you get it from the metal dust are this. Then we can have associated colloids. In associated, the difference between associated colloids and the uh, multimolecular colloids are that we know that multimolecular colloids individual particles are not stable, but in case of associated colloids, individual particles are very stable and they act as a solute, and you can make a solution out of them. But if you put a large amount, in that case they come together and form an association, and in that case they exist in the form of colloids, and we call them associated colloids. And these examples are the soaps and the detergents. Just a minute. All right. Now we'll discuss how can you make the colloids, general methods of preparation of colloids. General methods of preparation of colloids, so we can classify again broadly into 2 categories, physical methods and chemical methods. General methods of preparation of colloids. Okay. Physical method and chemical methods. Okay. In physical methods, uh, In physical methods, we can make colloid by grinding these substances to a very, very fine powder. Okay, but it is very, very troublesome because it has to reach to the level of the colloidal size. Okay, so initially in the primitive stage only people used to make it by using the grinding stones. Just like that, you have seen in villages how this atta is being made. They put the wheat in between the grinding stone, and they move the upper part of the stone. They move it, so it crushes into that. But in case of the um, colloids, there's two stones. Both the stones rotate, but in the opposite directions, and these are called colloidal. Colloidal. Okay, but this method is not an efficient method because in that case much of the substance is being wasted. But anyway, it is of historical importance. We should know that by using colloidal mill, you can grind the substances to the colloidal state. The second method is, it is preferably used, we call it Bradix arc method. This is being efficiently used. In that case, what you do? In that case, we take a container and we have here dispersion media. Okay, and we take two metal electrodes. Metal electrodes we put. Okay, and it's being immersed in a container containing freezing mixture. You can take ice and water. This is a freezing mixture. And high voltage is sent across this. Very high voltage. This is the we make the arc length. Okay. So when you see, there's no continuity there. So when you send high voltage across that, in that case, what happens? This metal, they become very, very hot. It becomes extremely hot, and the metal atoms are converted into vapors. So it comes to the, and that's because you have the dispersion medium. So immediately they get converted into colloids. So that is called British arc method. So this method is being used to prepare metal salts. You can make metal salts in the form of gold salt, silver salt, and other metals. So this is a physical method. Now, physical method is also known as, because another name is also there. We call them as dispersion method, and this is called condensation. In my copy, I have written this one: dispersion and condensation method. Uh, dispersion method is the physical method, and the condensation method is the chemical method. Now we'll go for chemical method. Chemical method, they are prepared by the normal chemical reaction. Chemical. Okay. So by chemical reaction, one is by oxidation. So in normal oxidation process we carry out. Say I have taken here H2S and bromine. Bromine halogen is an oxidizing agent. So you will get now here H here and you will get sulfur. And it will come in the form of sulfur. So this can easily be done in the laboratory. You take bromine water and to the pass H2O gas. Okay. Similarly, you can get it by sulfur dioxide. Okay. You can get it in the form of 2H2O and 3 sulfur. So this is also sulfur. Then by reduction. Okay. The reduction method, we prepare gold salt. Say I have taken here gold chloride. Gold has two valency, +1 and +3. +3 is more stable. We call it gold chloride or auric chloride. And this is being reduced by formaldehyde. When we go to organic chapter, you will find formaldehyde is a strong reducing agent. Okay. So this will reduce into gold. You get here formic acid and you get here HCl. So this is called gold salt. Gold salt. So we can prepare gold salt by British arc method. We can prepare by, or even gold can be reduced by a very strong reducing agent called stannous chloride. Stannous chloride. So you get now here this plus this is stannous chloride. This is also gold. Similarly, you can also get platinum salt. Okay. Then by hydrolysis. Hydrolysis is the reaction with water. Okay. Or when you can treat it with alkali also. This is can be very easy prepared. Suppose we have taken ferric chloride and we have taken here extremely hot water or steam. You'll find it is going to give you ferric hydroxide salt plus 6H. So it is ferric hydroxide Okay. Third, by double decomposition, that you know, this reaction you know it very well. Exchange of ion takes place. So in double decomposition method, we can take arsenic oxide and we'll pass here H2S. We'll take arsenic oxide as a suspension, it's not soluble in water, and through that we'll pass H2S gas. You'll get now here arsenic sulfide salt. Okay, this is called arsenic sulfide salt. Okay. So these are the physical and the chemical method. See, I told you that colloids can also be made by change of solvent. In some solvent, certain substance may act as a solute and form solution. Moment you change the solvent, you'll find in that case, that substance will be behaving like a colloid. Why I told you that if you have dissolved sodium chloride in water, it forms a solution. But instead of sodium chloride, to that if you add benzene, then you get sodium chloride salt. Reason also I told you, because sodium and chloride ion cannot be accommodated within the interstitial spaces of the benzene solvent. Whether in water the size interstitial size is large, so they can go inside and form a solution. All right. Then I'll come to a separate method. Okay. So this is called peptidization method. This is a third method. Mind it, I'm not putting OABCD. I have used uh, physical method and chemical method. This method is entirely different. We call it peptidization. This is important both for embossed and CVSC. It is a method by which a freshly precipitated substance can be converted to colloidal state by addition of small amount of electrolyte. Okay. Say I have taken here ferric chloride. To that I have added hot water. Initially I'll get here ferric hydroxide. This equation I have already written. So it will come as a precipitate, chocolate brown precipitate. To that you add ferric chloride solution dropwise. You'll find the precipitate has disappeared, but the solution is chocolate brown. That is, you get here now ferric hydroxide or salt. So this is called peptidation. Now let's see why does it happen. Cause of peptidation. See here. So this is ferrichloride water giving you ferric hydroxide. So they come down by force of gravity and precipitate. Okay. So it is precipitate. Now when I add ferrichloride is a strong electrolyte and is like this. Then ferric hydroxide absorb ferric ion. So what you get now here? Ferric hydroxide, ferric ion. If ferric hydroxide absorbs ferric ion. Now, if I write, suppose this is one entity. If I write here another ferric hydroxide with ferric ion, will they remain side by side? Will they stick with each other as they have stick in case of precipitate? Will it stick? Apply your common sense. Hello. See here, they have the similar charge. For similar charge, there will be repulsion. So immediately it will move away from each other. So the precipitate, which was the precipitate, was there like this earlier. So they will disperse to go to different places, and the sizes are bigger. So this is a precipitate, and this is a colloid. Right. So by the process of peptidation, dear, you can even change the charge of the colloid. Okay, that we'll discuss later. Now, see, in all these cases, we have prepared colloids. Maybe in one case we have used metal, but in all the cases we are using some chemical compound, salt or maybe something else. Okay, but always you'll find the side product is there. That is, it is impure. Side products are soluble in water, and colloids are not soluble in water. That is forming a heterogeneous structure. That is, it contains a lot of impurities. So, what are the impurities present in a colloid? We call that impurities present in a colloids are called crystalloids, because we know crystals are soluble in water. So you have to go for now purification of colloids. Purification of how you. So that was a challenge. See, particle size is bigger than solute. Okay. We have studied in solution osmosis. So when you go for osmosis, only the solvent molecule pass through. None of the ions present in the solution passes. So by using semi-permeable membrane, you cannot separate the soluble ions from the colloids. If you use the filter paper, in filter paper the sizes are bigger. So precipitate will be retained by filter paper, because precipitates are sizes of the precipitates are larger than that of the 1000 nanometer, or we call them their suspensions. Colloids will pass through. So that was a very challenging job. Huh? How to purify Collets. Now we find in the nature as well as you can make it. There are some membranes which allows the soluble solutes to pass through them. But the size of their pores is not large enough to pass through their holes. So these type of membranes are being used. All right. So first one we use it for dialysis. So what you do? Say I have taken a bottle like this, and bottom portion of the bottle I have cut, and I have used a membrane, and here I will have the colloid, impure colloid. Okay, and I'll immerse it in water. This membrane is initially made from pig's bladder. Okay, pig's bladder. Now you can make synthetically in the form of cellophane. Cellophane paper, all of you have seen. It's just like a plastic paper. Cellophane paper, you've seen it. See, if you put gum in one side of the cellophane paper, we call them a sellotape. So if you use cellophane in nature, you'll get this one also, parchment paper. You know, this is the first paper used for people for writing. It has been made from the papyrus plant of in the Egypt. You can use cellophane paper. You can use copper ferrocyanide. Okay, these are the substances you can use. So what will happen now? In the water, you'll find the impurities. Impurities are basically soluble salts. It will come out and the colloid will remain there. Okay, when I say it seems to be very, very easy, but actually it takes very long time and process is very slow. Initially it is faster, later on it becomes slow down because the concentration of the impurity near the bottom of the bottle becomes more and the movement becomes slow. So people are thinking how to increase this speed. See, we have also studied about the electrochemistry. What they have done? They have put two electrodes. They put two electrodes. We know the impurity presents are salts that is exist in the form of ions, and iron has a tremendous attraction to go toward the electrodes. So there is the force is being created. So by this way you'll find the anion will go to anode, anion will go to anode, and the cation will go to cathode. By this way process, the we speed up this process of dialysis, and that is called electro. Okay, electrodialysis. Mind this electrodialysis being used for the dialysis of the human kidney. Okay, kidney is there to purify our blood. When the kidney become ineffective, so in that case, what happens? The blood is filled with too much of impurity that is highly toxic to human body, and it may lead to people's death. So this type of electrodialysis is being carried out by the electrodialyzers. And what is being done to make the process faster? A pump is also being created, and these tubes are inserted here in the vein and is being put into the dialysis. So by that way, the blood comes out, gets purified, again goes to the goes down to the arteries. comes from the vein, goes to the artery. Okay. Now you know that we always want that to make the process faster. Electrodialyzer is found to be the dialysis unit is being used for the dialysis of blood. Now we want it to be faster. So different methods are being used. All right. So we go for dialysis, electrodialysis. Then we call it ultra centrifuge. In ultracentrifugation, the colloids are being put in test tubes like that. Okay, then this is the centrifuge. Okay, and the test tubes are there. And this in centrifuge, you have not seen centrifuge. Moment you switch it on, it will move with a very high speed. When you move it is very high speed, in that case, what happens? Colloids are larger in size than that of the solute, and by virtue of the centrifugal force, they get collected at the bottom and they settle down. And after that, we stop it, running for a few minutes, we stop it, then we decant the liquid. This colloid will not come out. It's almost sticking to the bottom. Then again, you put your solvent, again, we treat it for a few times. And by that way, you'll find it will be completely free from any type of impurity. So we can go for ultracentrifugation. Okay. Another method is there. It's called ultrafiltration. These are there in your book. Ultrafiltration method. Ultracentrifugation is not there, but ultrafiltration process. Yeah. So this is the filter paper. I told you the normal filter paper, the pore size is bigger. In that case, both the solute and the colloid passes. So these are the size of the. You just magnify, you can see. Okay, these are. If you put it below microscope, you can see the whole. So what we do? We put it in a solution of colloid. What is colloidal? Colloidal is nitrocellulose. So when you have dip this paper in filter paper nitrocellulose, what happens? Nitrocellulose settles at the pores and make them smaller. The size becomes smaller. All right. Then you take it out, dry it, and spray with formaldehyde. Why? To make it harder. Otherwise, it will get torn. Then you filter. In that case, this as you reduce the size of the holes, in that case, what will happen? The colloid will not go. The impurity in the form of crystals or solutes will pass. So by this method also, you can purify colloids. So again, let me summarize that what is dialysis? Dialysis is the purification of colloids by removing the crystalloid impurities. So dialysis, normal dialysis, what we do, we take some special membrane, which are the sizes of the pores, allow the solute particles to go through, but not the colloids. Okay. To speed up this process faster, we go for electrodialysis. In electrodialysis, we put 2 electrodes in the solution outside, and then that way the ionic impurity is present there, rushes out. Okay, then what you can do? You can go for ultracentrifugation and ultrafiltration. Okay, now we'll go for its physical properties. First, let us compare with the solution. So in solution, did you not read about the colligative properties? So what will be the colligative properties? Colligative properties of colloid. What is the definition of colligative properties of colligative properties? It has there are few physical properties of solution which depend upon the number of particles present in the solution, not on their nature. Okay. Now see here, and interesting. What is colloid? Say I have taken 300 molecules of C17H35. This. What is this? So why have written 300? Because I want to make it add more. We know soap. If you add soap in small amount, they behave like electrons. Suppose I have added there 50 molecules of this. So in solution, it will remain as 50. But where I added more, I told you they form associated colloids. So we find that maximum number of soap molecule can be present in maximum number which present is 100. As it is more, ultimately what will happen? What will find? You'll find 3 aggregated micelles. Now see here. In this solution, 300 molecules, they form an association and they exist as 3 aggregated molecules. They are inseparable. So 3 of them are there in three places. Here 50 of them are present in 50 different places. So as colligative property does not see what is the nature of the molecule, they are only going to count how many are there. The solution, what will find? In this case, it will find 50. So it is going to show you a colligative property of 50. But in this case, it is going to observe how many? It will observe only 3. So it is going to show colligative property only for 3. So what do you learn from there? You learn from there that the value of the colligative properties of colloids are less than that of this solution. So don't write this. This is what you can say, conclude. The value of the colligative properties of colloids are less than a dilute solution. It is because colloidal, let me put some ink. is because colloidal particles remain in aggregated form, and hence the number of particles in the solution become less. It is again an important question for exam. So this one will be on right. Write this. Okay. Tyndall effect. See, I don't know whether you have done or not, but we have, as we have grown up in villages, we had nights were very dark than that of town. And in villages, you find if you move from one place to another, as it is dark, so you have to use torch. Okay. So if you focus your torch in the dark night, you'll find lot of tiny, very luminous things are moving in the cone of your light. What are those? Because I told you air contains solid as dispersed phase and the gas as the dispersion medium. Excuse me. Hello, Biplov. ভালো ভালো ভালো। হুম হুম অ্যাড বুঝছি অ্যাড আমি তোর সঙ্গে করে না আমি একজন সঙ্গে যোগাযোগ করি। হুম কেন ফায়ার বিল্ডার আছে তারা কোচিং করেছে খুব ভালো। তুই তার সঙ্গে যোগাযোগ করলে it's not a question that you have done it for there, you can get it very nice work. হ্যাঁ তো তার সঙ্গে যোগাযোগ করলে করে গাইড করতে পারবো এবং ওর অনেক ছেলে মেয়েদের বিনা পয়সা ফর্ম ফিল আপ করবো। হুম ঠিক আছে। হ্যাঁ কোচিং ইনস্টিটিউট আমরা ওখানে পড়াই আমি মানবেরা বই পড়াই তখন তার প্রায় বন্ধুই আমি প্রায় 15-16 বছর আমি খালি কোচিং ওই এন্ট্রান্স কোচিং করি। স্টুডেন্ট নাম দিয়ে দেখতো প্রাইভেটের পেট্রোল বোর্ডের পিছনে আছে এক্স্যাক্টলি তারা একই ওয়ান সেক্রেট হার্ট। ফায়ার ব্রিগেডের ওই যে পেট্রোল পাম্পটার উপরে একটা গলি আছে না, কেন মেজিরও চেম্বার আছে, ওই দুটার মধ্যে যে রাস্তা গেছে এখানে। না না, এটা একদম ফায়ার ব্রিগেড। হয় হ্যাঁ। ওই ওই ঠিক মানে তারার ওয়াল আর ওই পেট্রোল পাম্পের ওয়াল। আমি তার সঙ্গে কথা হইয়া তার সম্পর্কটা করে শুনে তাকে মারতে পারবো। ঠিক আছে, ঠিক। So what happens? The in Tyndall effect, what is this? This is the scattering of light of the colloidal particles are called Tyndall. This scattering of light by colloidal particles is called Tyndall. So if you pass this light through a colloidal suspension, and if you observe it through a microscope, you will find bright speck of light is going on. Okay, so that is called Tyndall.
So Tyndall is D-A-double-L, sir.
Double L, yes. Sorry. The illuminated path of the light is called Tyndall cone. Can you come for Brownian movement? That generally cannot be observed by your naked eye. Okay. So it has been initially observed by a botanist. He has put the pollen of the flower on water, and he observed through microscope. He has found non-stop these pollen grains are moving above the surface of the water, and it is being named after him. It's called Brownian movement. We'll try to know why this thing is. So what you can say here, the ceaseless zigzag movement of colloidal particles is called Brownian. Now, why this type of thing occurs? What is the cause? It happens because of unbalanced forces of collision between the particles of colloids and molecules of dispersion medium. Dispersion medium molecules are more in amount number and they are less in number. So the collision which takes place, due to this collision, the colloidal particles cannot stop their movement. Continuously they move. So it is the unbalanced force of collision. Okay. And because of this, colloidal particles never precipitate. Okay. So this is one of the reason of stability of, because moment they precipitate, then now moment they precipitate, they are no longer called color. They'll be called suspension. Even if they want to come also, the solvent molecules push them back. Many of these colloids are colored. Why it is colored? Because of the scattering. When it scatters, the light comes out with a different wavelength. Again, the color of the colloids depends upon from which side you view it. Suppose this is a colloid and this is the incident light. Colloid is there. So the portion of the light will be reflected. So this is a reflected light. This is the incident light. And some portion will come out. This will be refracted. So you'll find the color of both of them will not be same. So it depends upon their wavelength. This experiment you can also see at your home. We know that the milk which is being provided to us by milkmen, most of them are not honest. They put water. Some may put less water and some may put more water. And if you tell him, he will deny that I did not put water, it is like this. But just by the view itself, you will be able to see. So what we'll do, suppose you have taken in a container, you raise it near almost little bit below your eye level. And you try to see. You find the white milk is having a bluish tinge. If you are not able to see, just tilt it. You'll find small waves of in the milk will be created. Ripples will be created. You'll find on the edge of the ripple it is having a blue tinge. That is, he has poured more water because milk is a emulsion. Is a colloid where dispersed phase and dispersed medium, both of them are liquid. But if it is being observed through a microscope about the refracted light, you will be scared to see this is red, this is blue, this is red. So if it is milk, this is blue and this is red. So it depends upon two factors. One, the wavelength of the light which is either reflected or refracted. And second is the size of the colloids. If the size of the colloid changes, then the color also changes. Wonderful thing is observed in case of gold salt. Please remember that gold, though you know it is yellow in color, but the gold salt does not have, initially does not have yellow color. Okay. If the gold salt is very fine, then you are going to observe a red color. And as the size of the particle increases, it will turn purple, then blue, and finally yellow. With these different types of beautiful designs are being made. Okay, different articles are being made where we can see. They'll put. You'll find they're going to put this gold soul in a glass jar, and inside that glass jar they'll put a electric bulb. Okay, initially to a naked eye, it will look colorless. Moment you switch on the light, you'll find it's either red or it is purple or it is blue or it is yellow. So it depends upon the size of the particles of the gold. Silver. Weightlifting. Okay, just give me 1 minute. Charge on color. See, most of the colloids are charged. Most of the colloidal particles carry either positive or negative charge. Most of them, especially the I told you that lyophobic colloids are not stable. So we induce charge on the lyophobic colloids. Others will settle down because they are unstable. Okay. Yes, because they are having charge. So the colloidal particles never stay together, because if they stay together, it will precipitate. So they remain far. So don't precipitate. So on the basis of that, we can have positively charged colloid and we can have negatively charged colloids. All right. Open your book. You will find charge on the colloid. Open it. See the examples. Have you opened the book? Hello.
Yes, sir.
Acha. What are the examples that given on the what are the examples for the positively charged colloids? Tell me the example in the box they have given. What they have written? Positively charged. What they have written? Metal hydroxide salts. Is it? Tell. Hmm?
On the positive, hydrated metallic oxide.
Then
On negative is metal.
yes, metal salts. Okay. Then other than that, what are the examples? Blood. Blood comes in which category? Positive or negative? Hmm?
Positive.
So blood, and they have mentioned about any muddy water. Hmm?
Yes, it dye stuff.
Yeah, this, forget about the dye. These are the things which you can see. This one we have seen, this one we have seen. This you have not seen, this also you have not seen. Okay, so they carry positive or negative charges. I have already shown you how it has become. I have shown you the example of metal hydroxide salts, ferric chloride. Then to that you have used very hot water. Then it has become ferric hydroxide precipitate. Okay. So I write here now S precipitated. To that when I add ferric chloride, ferric hydroxide has absorbed ferric ion and you have got positive colors. Because of that, this precipitate has become a colloid. The process is called peptidation. Okay. Now, this you have a liberty to make positively charged colloids or negatively charged colloids. See, the same one, if I don't add water, if I use sodium hydroxide, then what you are going to get? You will get the same thing, ferric hydroxide. Okay? I'm not writing that up. Okay, I'll write that here. 6 Now, sodium. Now, if you have added little more extra amount of sodium hydroxide, see now, it is going to absorb hydroxide. So you are going to get a negative color. That is, you have the liberty to make. Okay? So this is the way we can make the positively charged colloid and negatively charged colloid. In your textbook, they have given example of the silver iodide. Silver iodide. They have taken silver nitrate and potassium iodide. When they add excess of silver nitrate, then the silver iodide absorbs silver ion. It becomes a positively charged colloid. But if they have added excess of the potassium nitrate, potassium iodide solution, then silver iodide absorbs iodide ion and it becomes a negatively charged colloid. Okay. So let me show you to the diagram. See here. So this is the ferric hydroxide. It has absorbed ferric ion. It has absorbed ferric ion. Now ferric ion cannot go. It is absorbed. But see, as a whole, any substance thing that we make in our chemistry, as a whole, the solution is neutral. We have made a colloid, but the solution which contains the colloid is this neutral. Why it is neutral? Because ferric chloride has 3 silver ion. Chloride ion. So this chloride ion is floating around this. So this is the fixed layer because it is absorbed. And this one, it moves around. So this is the moving layer. Because of that, the whole colloid is neutral. So obviously, between a positively charged layer and negatively charged layer, a potential difference will be there. So the potential whatever, we don't right. Between the fixed layer and moving layer is called electrokinetic potential or zeta potential is important. Okay. Now, see, if I have taken an electrolyte, this is a cathode, and this is an anode. Okay. Okay. So all the cations will move here, and all the anions will move here, and we put electric potential. Okay. What do we call it? We call it electrolyte. Anions lose electron, and it comes here, then the metal gains electron, and you get metal, and here the non-metal happens. We call it electrolyte. Now, same thing if you do. Okay, which color? This is cathode, and this is anode. So what will happen now? Positive charge colloid will go to cathode. Okay, and the negative ions will, suppose you have taken ferric hydroxide colloid, ferric hydroxide plus Fe3 ions will go there. What will happen now here? Ferric hydroxide Fe3 plus will go, and the chloride will come here. So what will happen now? Same type of thing is going to occur. So in that case, we call this to be electrophoresis. Electrophoresis. See, suppose it is ferric chloride. So it will go here, ferric 3 plus, CCl minus, then cathode, and here this one will give you 3 chlorine plus 3 electron, and Fe3 plus you'll find, sorry, I should have written here. 3 Cl will give you 3 chlorine, 3 electron, and Fe3 plus will take 3 electron and become iron. So iron will deposit, and the chlorine will go. In this case, what is going to happen? Here you will find 3 chlorine. Sorry. 3 chlorine will be here, 3 electrons. Here FeOOH, Fe3 plus will take 3 electron, and what you are going to get? Ferric hydroxide is lose its charge, iron will be deposited there, and this will precipitate. Please remember, when you carry out electrophoresis, the precipitation of the colloids takes place, and the process is called electrophoresis. So with this, I finish today's lecture.
Done, sir.